Today's goal is to use summation notation to expand and evaluate series. Well, what's a series? A series is simply a sum of terms in a sequence. And summation notation, well, this is how we note or write down a series, which again is a sum of terms in a sequence. Let's take a look at a couple examples. Here we go. Example 1, evaluate 3 plus 6 plus 12 plus 24 plus 48. We say it's a series because we're adding up a bunch of terms, and the terms themselves follow a clear pattern. So these are terms that come from a sequence. So if we're adding these up, you can just use your calculator. Type it all in. I think you get 93. It's no problem. It's pretty easy. Okay, let's take a look at this next example. Evaluate 3 plus 6 plus 12 plus, Well, I can see the pattern still holds. So one way to do this would be to say, okay, what are the missing terms? We've got to figure them out and then include them when we're adding them up. 192 plus 384. Again, you can just type this giant thing into your calculator. You get 765, no problem. It's not that hard. But sometimes that process gets annoying, right? Look at example 3. I haven't yet found the missing terms, and I certainly can find the missing terms, but there may be a lot of terms in between. So for all the work it would require to find all the missing terms and then type them all into my calculator and double check that I typed everything in correctly, it becomes a little bit tedious. And so that's why we have summation notation, which is also sometimes called sigma notation. I like to think about summation notation as this. You've got this Greek letter sigma, that's why we sometimes call it sigma notation, and it's kind of like taking each and every one of these terms, right? We've got a 3, we've got a 6, we've got a 12, we've got all these terms, and it's sort of like folding them up, right? Like how these post-it notes, each post-it note stack is made up of many, many, many individual pieces of paper or many individual post-it notes, but you can sort of fold them up into one small stack or one sort of easier to work with notation. So this sigma notation, we're going to write the definition of the sequence, which is 3 times 2 to the n. We can see that because our initial term is 3, and the pattern is there's a common ratio of 2. Okay, so that explicit definition of the sequence is what goes to the right in my sigma notation. And then under my sigma notation, I'm going to say, what's the first number you sub in to get the initial term in your series? Well, we see if you sub in 0, that would be 3 times 2 to the 0, which is 3 times 1, which is 3. Okay, so we have to substitute 0 in to this explicit definition in order to get the first term. Well, the number here is the number you sub in to get this last term in the series, which I don't currently know. But we could figure that out. We know that this term, 196608, must be a member of the sequence 3 times 2 to the n. So this is just an exponential equation, which we know how to solve. We're going to isolate the base, substitute or turn it into a logarithmic equation, and we get that n is 16. And you can check if you want, right? Make sure 3 times 2 to the 16 really does give you 196,608. Okay, so that works. So we're going to put 16 here. That's like saying we're taking all the terms that have this shape, 3 times 2 to the n, where you're first going to substitute in 0, last going to substitute in 16, and then this big sigma tells you add them all up. Well, lucky for you, you can do this in your calculator. In your calculator, you're going to press the math button, which is here. It's going to pull up a menu that you can scroll way down to the bottom until you see this summation. It's option number 0. It's going to pull this up on your calculator. It looks like this. I'll blow it up. It has some dash boxes. Now your calculator, I'm not going to use n on because usually that's a stored value and we just don't want to play with that. So I'm going to use the x button, that variable button that's right here. Type x equals here, and we're going to put 0 here and a 16 here. You're using the arrows on your calculator to move between these, and 3 times 2 to the x. When you press enter, it's going to give you that sum. We found out that this sum is equal to 393,213. And if you have a different kind of calculator, please see your text notes for directions for what you're actually typing to get this sum in here. Okay, let's look at a few more examples. Example 4, evaluate this series, this sum, by hand and using technology. Now this sum is usually written with n equals 0 to 5 up on top. So we would say this is the sum of the terms 3 plus 2n from n equals 0 to n equals 5. So evaluating it by hand means we just need to expand the terms. So this is telling us first you substitute 0 into this thing. So this would be 3 plus 2 times 0. Then you keep substituting all the way up to 5. So this is a little bit tedious, which is why we have a calculator to do this for us. So I'm substituting in consecutive terms between 0 and 5. So 3 plus 2 times 0, that's just 3 plus 5 plus 7 plus 9 plus 11 plus 13. And you'll get 3 plus, let's see, this would be 10, this would be 20, plus 18, so 38, 48. Okay, and lucky for you, we can check it using technology. Go ahead and grab your calculator, type this thing in, and you should get the same answer. Okay, last question of the day. This is just one more notation you'll need to know. S sub 10 means the sum of the first 10 terms in the sequence. So I like to think of S sub 10 as meaning you're going to take your initial term, and the first term after that, and the second term after that, and so on. If you're adding up 10 terms, that would be an initial term all the way through the 9th term after that. Okay, and we're given this sequence 0, 1, 4, 9, 16. Oh, these are perfect squares. So we're going to use our calculator. It's the fastest way. And this just looks like n squared, where n goes from 0 up to 9. 10 terms would be the initial term plus 9 additional terms. When you type this in your calculator, please double check that you get the sum 285.